In video 67 of Tensor Calculus, we'll follow up our last video by demonstrating what the projection operators look like for each of our sample surfaces. We'll start with our cylindrical surface. We said that our normal projection operator is defined this way. It's just the various combinations of all of the vector components of our normal vector here. Now, we've expressed our normal in Cartesian coordinates, so remember that means that the contravariant components and the covariant components are the same. So ni in the upper position, the same as ni in the lower position. Okay, and also, since there's no z term, let me add that on here this way, just for completeness, so we remind ourselves that there are three components, but the third one is actually 0 right here. Okay, now this result then for the normal projection operator can be done almost by inspection. So let me just display it like this, and then we'll show you how it comes together. What we have here is we're going to multiply all the possible combinations of our normal vector components. So P11, this guy right here, is just the product of this component times itself. All right. P12 is this component times this one, giving this. The third component is this one times this one. So we're simply going through each of the possible combinations of these vector components of our external normal. So the second row, we'd take n2 times n1 to get this. We'd take n2 times itself to get this, and n2 times n3 to get this one. And then the last row is just n3 times n1, and n3 times n2 to get this, and n3 times itself to get this. So forming this normal projection operator is a pretty trivial exercise. This is the result for cylindrical surface. All right, let's check out a couple of our identities. We said that this is an identity, that PII is equal to 1. So PII is just P11 plus P22 plus P33. In other words, this expression is just the sum of our diagonal elements running down this way. So cosine squared theta plus sine squared theta plus 0 is equal to 1. So that identity is validated here. Okay, what about this guy? We said if we contract this normal projection operator with itself, we'll get the normal projection operator again. Well, to demonstrate that, let me copy our normal projection operator down a couple of times like this. So here I've just copied this down in these two locations, and we'll multiply this matrix by this one. So to form this contraction, we're just going to multiply this projection operator times itself. Okay, remember how this works. We're going to use this row and this column to give us this entry in our result here. So we have cosine squared theta times cosine squared theta is cosine fourth theta. Then we multiply this item times this one, which is sine squared theta cosine squared theta. And then this element times this one, which of course is 0. Now we can factor out the cosine squared of theta, leaving cosine squared theta here, and sine squared theta here. And of course this value in the parentheses is 1, so this entire expression resolves down to simply the cosine squared of theta. So that's the value for item 1, 1 in our result. Okay, the second item in the first row up here is going to be this row times this column. So that is sine theta times cosine cubed theta. That's this item times this one. And now to that we're going to add the product of this one and this one, which is sine cubed theta cosine theta. And you can see that we have a common factor here. Of course, 0 times 0. The third term 0, so we simply skip that one. So here we can factor out the sine theta, cosine theta, leaving cosine squared from this term, and the sine squared theta from the second term. And of course, again, this factor is 1, leaving us with the result of simply sine theta, cosine theta in this position. Okay, next one, we'll have this row times this column. Well, all of these are 0, so this times 0 plus this times 0 plus this times 0, the whole thing is equal to 0, so this item over here is just a 0. Okay, next one would be this row right here times this column. And that's going to be sine theta, cosine cubed theta, plus sine squared times this is equal to sine cubed theta times cosine theta. And we've done this a couple of times already. You see where this is going. We can factor out sine theta, cosine theta, leaving us with cosine squared theta plus sine squared theta. So this whole thing is simply equal to sine theta, cosine theta here. All right. Next one is going to be this row times this column. That's going to be sine squared theta, cosine squared theta, plus this term times this one, which is the sine fourth of theta. And of course, we can factor out the sine squared theta, leaving us again with a factor of cosine squared plus sine squared being equal to 1. So that tells us that this second term here is just sine squared theta. All right, next one is going to be this row times this column. Well, again, everything is 0 because we're multiplying this times 0, this times 0, this times 0. So that result is just 0 right over here. Okay, and finally, we're going to have this row times this column. Everything here is 0, so it's easy to see that we have simply zeros here, here, and here. And with that, you see that we have confirmed this identity because this is exactly the same as this and this. So the contraction of the normal projection operator with itself gives us the normal projection operator. So this is confirmed. All right, let's move on now and take a look at the surface projection operator. And for that, you'll remember that this is our formula. We said that our surface projection operator, Tij, is going to be formed by the contraction of our shift tensor with the inverse of the shift tensor using the surface index as the dummy index like this. All right, we're going to need a little more room, so let's go work on this separately. Let's start by reminding ourselves of what it means to contract the shift tensor with its inverse along the ambient index like this. Now, if we were doing this in linear algebra, what that would mean is that we're going to be multiplying a matrix that has 2 rows and 3 columns by a matrix that has 3 rows and 2 columns. And if you remember in linear algebra, this number right here, this guy, has to match this one in order to be able to do this multiplication. And the resultant over here is going to have a dimension of 2 by 2. That means that we're going to be multiplying each of the items in this row by each of the items in this column. We'll have 3 different products. Adding them together will give us an entity here. We'll do the same thing for this row, this column, to give us this entity, and so on. So let's just do it real quick. What we're going to have here is we're going to have this row by this column. And so that's negative 1 over a sine theta times negative a sine theta is sine squared. This term times this one is cosine squared. Sine squared plus cosine is 1. 0 times 0 is 0. So this first term right here is equal to 1. All right. Then we'll take the first row times the second column. This times 0 plus this times 0 plus 0 times 1 obviously is equal simply to 0 right here. And then next we'll have this row and this column. That's 0 times this term, 0 times this, 1 times 0. All of that is equal to 0. And finally we have this row times this column. 0 times 0, 0 times 0, 1 times 1 leaves us with a value of 1 right here. And so as expected, the end result right here is our identity matrix, which in tensor calculus, of course, is just the delta function. And it's got indexes of alpha and beta, which means its surface indexes. It's a 2 by 2 matrix. Okay, so now contrast that with what we have to do to find the surface projection operator. We're going to contract the shift tensor again with its inverse, but this time it's going to be along this surface index right here. So if we look at it again in terms of linear algebra, what we're doing this time is multiplying a matrix that has 3 rows and 2 columns by a matrix that has 2 rows and 3 columns. And that means that the dimension of the resultant over here is going to be 3 by 3. So there'll be 3 entries, 3 rows, and 3 columns over here. And it means that each of these items, these components over here, are going to be made up of 2 products. We'll be multiplying, for example, this times this plus this times this. So there'll be 2 products added together in each case to give us 9 components over here. Okay, so let's just do it. First, we'll have this row times this column. So negative a sine theta times negative 1 over a sine theta is just sine squared theta. And then 0 times 0, of course, is 0. So that leaves us simply with sine squared theta as the first component. All right. Next, we're going to have this row times this column. And that's going to be negative a sine theta times 1 over a cosine theta. That's just negative sine theta cosine theta. And again, the second term is 0 because it's 0 plus 0 times 0 right here. So our second item in the first row is negative sine theta cosine theta, like that. Okay, now we're going to have the first row times the third column. This term times 0 plus 0 times 1 is, of course, just equal to 0 out of here. All right, so now we're going to have the second row times the first column, and that's a times negative 1 over a, and then sine theta cosine theta. So this term, again, and second term is 0 times 0. So this, again, is negative sine theta cosine theta, like that. Then we'll have the second row, second column. That's a cosine theta times 1 over a times cosine theta is cosine squared theta plus 0 times 0. So this term is the cosine squared theta. Then we'll have the second row, third column. This term times 0 plus 0 times 1. That's easy. That's just 0. Then we'll have third row times the first column. 0 times this term plus 1 times 0 leaves us with a 0 here. Then we'll have the second row, second column. 0 times the first term plus 1 times 0 is again 0 here. And finally, second row, Second column, 0 times 0 plus 1 times 1 leaves us with a 1 right here. So this is the end result right here. This is the surface projection operator for a cylindrical surface. Notice again that the result is a 3 by 3 matrix, and it is not the identity matrix. We get the identity matrix up here, but not when we find the surface projection operator. So now we can add the surface projection operator just like this. This is what we just derived a moment ago. Okay, let's check out some of the identities here. Remember, we said that the contraction of these two indexes for this operator should give delta alpha alpha, or value of 2. Well, this is just like the projection operator up here. This is just the sum of the diagonal elements. So if we add these together, sine squared theta plus cosine squared theta is 1, plus 1 gives us a value of 2. So that confirms that this identity is true. All right, we also said that contracting this operator with itself gives the operator again, same idea as this, and we could confirm this exactly the same way. We just multiplied this matrix by itself and you'd find that we get the same result again. I'll let you do that on your own. I won't waste video time doing that here. Okay, but let's look at this final identity, the one that says the sum of these two operators equals the delta function. Well, that means when I and j are equal, the sum of the two operators should be equal to 1. And when they're equal, that just means the diagonal elements. So it means that if we add P11 to T11, we should get 1. And in fact, we do. All right, if we add P22 to T22, we should get 1. And again, we do. Sine squared plus cosine squared. And then we add P33 to T33. We're adding 0 here to 1 there. So the sum of these diagonal elements added to their corresponding values here gives 1 in every case. All right, but it also means that when I and j are not equal, then the sum of these two should be 0. That means that P12 plus T12 should equal 0, and it does because we have the opposite sign. And of course, 0 plus 0 is 0, 0 plus 0 is 0. Going down the other way, this one plus this one is 0, this plus this is 0, and this one plus this is 0. So all of that shows you that this identity is in fact correct. With that, let's move on now and look at the spherical surface. All right, well again, we just apply our formula here. We're going to find the various products of our external normal vector components here. So the result looks like this. This item by itself gives us P11. 1 times 2 gives us this. 1 times 3 gives us this, and so on. Second times the first gives us this expression. Second times itself gives us this one. Second times the third gives us this one. And then this times this gives us this. This one times this is this. And this times itself gives us that. So it's just a matter of running through all of the various combinations. Now I'm going to let you validate all of the identities here. I won't go through all of that again. Now to find our surface projection operator, of course, we have this formula. But this time I'm going to cheat because we've already shown this identity and how that works. So rather than go through this product, which is somewhat involved, we can simply apply this identity and reverse engineer the result using this expression. So let me just display it here and you'll see what I'm talking about. For each of the diagonal elements, I simply am going to subtract these items, this one, and this one, from 1. So this is just 1 minus this expression. This is just 1 minus this expression. And this is just 1 minus cosine squared theta. So I can get the diagonal elements just by subtracting each of these from 1 respectively. And then everything else is simply the additive inverse. This is the negative of this. this is the negative of this is the negative of that, and so on. Same is true for these three being the negatives of each of those. So applying this identity gives us a much easier way to derive this directly from the normal projection operator like that. Okay, and again, I'm going to let you confirm all the other identities concerning the surface projection operator. So now let's move on finally to look at the torus. Okay, for the torus, we go through the same drill. We simply multiply each of the possible combinations of our external normal vector components up here. So 1 times 1 is going to give us this. 1 times 2 will give us this one. 1 times 3 gives us this one, and so on. Second times the first is this. Second times itself is this one. Second times the third is this one. Third times the first is this. Third times the second one is this. And the third times itself gives us this one. Okay, then for the surface projection operator, we use the same shortcut we just did for the spherical surface, and that's this. We use the diagonal elements on our normal projection operator and subtract each of them from 1. So that gives us this subtracted from 1, this subtracted from 1, and this subtracted from 1. Give us the diagonal elements on our surface projection operator. And everything else is just an additive inverse. This is the negative of this one is the negative of that, and this is the negative of that. And likewise, these three are the additive inverses of these three. So it's that simple. And with that, we have the projection operators for the torus, and we are done. We have successfully demonstrated the projection operators for each of our sample surfaces.